Hello, everybody. We are here with our 6th webinar with RATS, Rotating and Turbomachinery Society. We have here MAN Energy Solutions, and Ralph, our technical director, is going to introduce our speakers for today. So go ahead.
Yes, welcome everyone to our next technical presentation. Hope you enjoy this one. We are doing these monthly, and we have Alberta Governor scheduled for next month, November 19th, and going into compressor controls. Today we're going to hear from MAN, and starting off will be Martin Shironoshita, and he's the regional sales manager for Canada for MAN, for PrimeServ, which is the aftermarket side. He resides in Edmonton, Alberta. He's been with MAN Energy Solutions for 3 years. He has over 20 years of industrial experience and over 10 years of experience with rotating equipment. He has particular experience with mechanical seals as well, and seal support systems. He has his Master of Science in Mechanical Engineering. So I'll turn it over to Martin, and he'll start off, and then turn it over later to our second speaker, Marco.
Thank you very much, Ralph. If you wouldn't mind then changing it to the presentation, Andrew, please. There we go.
Okay, Marco, there you go.
Yeah, okay. Well, welcome everyone. Thank you very much for joining us. As Ralph said, my name is Martin. Don't worry about the last name. I am located in Edmonton, Alberta, and we are MAN Energy Solutions, formerly known as MAN Diesel and Turbo, formerly known as MAN Turbo, which is a name that I hear quite a lot from my contacts here. So very quickly for you, the history and timeline that we have, MAN really goes back a lot in history, all the way back to 1758, which is when we formally consider our founding date. And then as time went through and mergers happened, we incorporated brand names, legacy brand names such as Borsig, GHH, which then became GHH Borsig. And then on the other side, you see the Sulzer bracket, which was Eschervis, which then joined Sulzer. Sulzer joined with Bramboveri, became BST. Then they separated part of the BST part into the ABB stream, and then Sulzer Turbo left with some of the turbines and compressors, and then Sulzer Turbo was basically joined with MAN around early 2000s, and that became MAN Turbo at that time. And then through the time just changed to MAN Diesel and Turbo to incorporate the diesel engines division that we have. And currently MAN Energy Solutions, with our focus into newer energies, renewables, right, and really looking at a path to the future in energy. So that's hopefully that's a very brief and quick overview of our history and the legacy brands that we actually currently now own. So we are the OEM, and we own the intellectual property of all these legacy brands. So if you have any equipment that's branded GHH, any compressors that are branded, or some turbines that are branded Sulzer, mind you, not pumps, but compressors that are branded Sulzer, those are now, of course, intellectual property of MAN, and we have all the capabilities to provide the support on those. So with that said, there is a question, if you wouldn't mind, Andrew, now going to the poll, something that we would like to have you guys answer.
Okay, so far I see just over half people have responded. We're getting up there to about 70%, 75%. Thank you very much. We'll close the voting in a couple seconds. A couple more last minute ones coming in. And that's good enough for now. I'll close the polls now.
Okay, so over half didn't know that we are the OEM, which it is compatible or consistent with what I also found in the industry. So hopefully this will be a reminder. Now you guys will know that indeed, if you have equipment of this brand, we are the OEM. We have all the information, history, records on these machines, designs, drawings, and we are definitely suited to support you on those machines. So thank you for providing that feedback. It's good to know. So with that said, then keep in mind, again, these brand names. Marco, if you could go to the next slide. Just so you can see between our turbomachinery, but also our marine engine division, which is the other big part of our organization. Now we have a fairly large global footprint and quite a bit of a presence in Europe, Middle East, Asia. Here in the Americas, we are getting quite a bit of traction here now with a bit more localized support as in the person of Marco, as a matter of fact. So just a quick snapshot of how wide our network is and our capabilities to properly support your turbomachinery needs. So with that, I would like to turn it over to Mr. Marco Schwarz. Marco Schwarz is our head of engineering in our Texas facility located in Brookshire, Texas, a brand new state-of-the-art facility that we opened about a couple of years ago, and where we are suited really to service your turbomachinery repair needs and service needs. Marco, as I said, is our head of engineering for all of the Americas, based out of that office. So he supports not just North America, but also all of Central and South America. He has plenty of experience with MAN. He comes from actually our Zurich product center, so he has worked directly on some of the design, some of the direct engineering and evaluations and calculations on our compressor train. So very experienced person, knows particularly the machines that come out of Zurich inside and out. So with that, I will turn over to Marco.
Thank you, Martin, for that introduction. Ladies and gentlemen, welcome from my side as well. Thanks for joining today. I'm going to dive into revamping turbomachinery today. And I would like to start off with a pretty simple question. Why revamping turbomachinery? Well, if your mics were open for these webinars, I would take your answers, your response. However, this is not the case for this setup. So I just would like you to spend 3, 4, 5 seconds about that question. Why is it necessary to revamp turbomachinery? This is the answer. It's about money. Well, that's the main answer. However, of course, there are several other reasons why turbomachinery can and should be revamped. And I'm just going to mention that in the following couple slides. But first of all, I would like to give you guys a short introduction about background, about reasons for revamping as mentioned. Then we do have the technical aspects about axial compressors, centrifugal compressors, what and how can equipment be revamped. Then we talk about MAN OMNICARE. This is how we call it, and it's basically about modification on equipment which has been supplied by suppliers which are not in the market anymore. And last but not least, of course, we do have time for discussions or for your questions. Having this said, I'm going to start and dive into the introduction about reasons for revamping turbomachinery. Well, one of the main points, the main reasons for revamping turbomachinery is that there has been an increased demand for the end product that any manufacturer provides. This can be refined products, it can be plastics, it can be air separation, whatever business we're talking about. There's very often just an increased demand of the end product, which then results in an increased demand and increased performance of the turbomachinery equipment in the corresponding plant. Another one, efficiency improvement, emissions reduction, a topic that becomes more and more important or became more important over the last couple of years, and it will become more important in future. Furthermore, we handle a lot of natural gases, and natural gases do have the tendency to change over the years. So basically the composition of the gases in a gas field somewhere around the globe is not going to stay the same throughout the whole existence of a gas field. So they change, and if the gas composition change majorly, equipment, the turbomachinery equipment is not capable to suit it anymore and needs to be adapted accordingly. New power sources are another reason. So there are times when it makes sense to switch from a steam turbine to, for example, an electrical motor to drive the compressing equipment, or it can be the other direction, or it can be gas turbines to replace by electrical motors, or vice versa. Adapted process demands. The overall process in a plant, it just change due to modernizations, adaptations, which then results in adaptations on the process conditions of the turbomachinery equipment. And last but not least, gas field pressure decreases. As mentioned, many of the compressing equipment is installed in the oil and gas industry, and the pressures in the fields, they just drop over the years of production. That means the compressing equipment needs to be adapted accordingly. A higher pressure ratio is required, and that can result in modification of the equipment as well. What are the benefits in general of revamping turbomachinery? First of all, as mentioned, one of the biggest drivers is usually financial savings and earnings. Reliability, efficiency, increased production eventually ends up in the dollar values. Besides that, the Green Deal, reduction of emissions, energy savings, it's becoming more and more important throughout any industry that turbomachinery is installed. Furthermore, there are technical reasons. There can be an optimization of the production, safety, or it's just to adapt the equipment to state-of-the-art design, or just minor changes to the equipment and reuse of the main existing components. We're going to dive into that a little later for a little more. Last but not least, there is the human factor, which shall not be neglected. Operating personnel sometimes is used to equipment for decades. Consider the fact turbomachinery might operate for 50, 60, 70, or even 80 years in the same place, and certain procedures are established, and it's not that easy for on-site staff to just adapt to a completely new turbomachinery equipment with completely different behavior. So that can result in unforeseen shutdowns and difficulties when the equipment is just completely replaced by something new, and it might be worth to just replace parts of it and modify the existing equipment accordingly. In summary, it can be said that costs of revamping turbomachinery, and we're talking about rather major revamps as shown here, for example, on that axial compressor, all the green internal components of that compressor. The prices are usually in between 50 to 70% of the costs of a new machine. Now, one could ask, why should I invest 50 to 70% of the price of a new equipment into that old equipment? The answer is basically shown here at the lower left corner. Installation costs are way, way lower when the main components of the existing turbomachinery can be retained. Let's say the outer casing remains in place as is, so we do have a very short shutdown. That means open the casing, remove the old parts, install the new parts, close it back again, and ramp up, and you're back in operation. Instead of replacing the whole casing, usually results in adaptation on the pipeworks, foundation needs to be reviewed, and there are always certain things coming up during these replacements. So the standstill and shutdown times are much longer, and this usually results in significantly higher costs. Now we're going to dive into the technical part of that presentation. I'm going to start with the modification of axial compressors. You saw a pretty similar sketch drawing of an axial compressor just a few slides earlier. This is the inlet nozzle, here the flange, and we're basically feeding throughout the inlet volute into a certain number of axial compressor stages, which usually consist of a rotating blade and a stationary vane. The medium, mainly air, is compressed, fed through the diffuser in the discharge volute, and then fed to the downstream pipeworks and the process. What we're going to look at in specific is that internal part of the axial compressor. Call it the thermodynamic or aerodynamic part of the equipment. Looking at this specifically, we do have a certain setup in original performance maps. As you know, performance maps are usually shown either flow versus pressure, discharge pressure of the unit, or we do have flow coefficient versus polytropic head. They basically mean exactly the same. I use pressure versus flow because it's a little easier to understand. So what you can see here in red is the given layout of an existing compressor. The envelope and the compressor can operate. Let's talk about modification of that existing compressor. The easiest thing to do actually is to change the rotating speed. Lower the speed or increase the speed. The question is, what is the impact on the performance envelope when changing the speed? When changing the speed of a compressor, it can be said in a first approximation that we shift the envelope along the surge line from the bottom left corner to the top right corner. It's important to know that we're not shifting the map upwards or downwards. So we're not really gaining any higher pressure ratio. We gain a higher pressure ratio, but that higher flows only. So it's pretty simple. We just shift the map along the surge line. What's seen here in blue is when we're increasing the speed, we're going to shift to the upper left or upper right corner. Besides that, another common revamp option to revamp axial compressors is to adapt the stages. That can be replacement of the stages by a different blade design, by a different type, or in order to keep costs low, additional stages can be installed or just removed. So the question is, what happens if we're gonna, as shown here, for example, we're gonna add an additional stage which consists of a rotating blade and a stationary vane on that compressor. How does the performance envelope shift? In this case, the envelope shifts upwards. Adding stages means we increase the pressure ratio. That means we lift the discharge pressure. That's the only thing we're gonna do. If we remove stages, of course, we're gonna lower the pressure ratio. So we can say we adapt the performance envelope or we move it vertically, but there's no horizontal movement to lower or to higher flows. A bigger revamp modification that can be done is to exchange the flow channel and the blading. Of course, that ends up in higher costs. However, it offers way more flexibility. And as an example here, it is possible to shift the map to higher flows or to lower flows if the unit is oversized, less flow is required, and we want to avoid recycling throughout continuous operation. Last but not least, of course, the combination of all of those options. That gives us the biggest flexibility, and we can gain quite a bit of an envelope and a range of modifications that can be applied to that existing equipment. Another thing, revamp option that comes up pretty frequently is the replacement of hollow shaft design rotors by solid shaft design rotors. Back in the days, we're talking about the 60s, the 70s, sometimes the 80s, many of the compressor shafts were made of a hollow shaft design. Reason for that was basically it was lighter. Material costs were much cheaper. Nowadays, I'm not aware of one single manufacturer for major equipment that still builds hollow shaft rotors like we did in the old days. And there are some reasons for that. The downside, of course, is we're going to add weight. We can consider about 50% of weight increase when talking about an axial compressor shaft. However, the pros about it is we do have simpler manufacturing, and this is the main cost factor that makes it less expensive. We do have much better rotor dynamic stability because the equipment is heavier, it runs more stable, and we have lower sensitivity to corrosion. That might sound special, however, if you consider the hollow shaft design, they're either welded or screws, and there's always space and weak points where corrosion can start and can be initiated. With the solid shaft design, these weak spots are basically gone and not present anymore. At the downside, as mentioned, we build heavier. That means the existing equipment needs to be checked if they can handle that additional 50% of weight. Is there any impact? Do we have to exchange the bearings? Is there even bearing housings that needs to be exchanged? And of course, the transportation of the equipment to site. However, considering that the equipment might be running for 30-40 years, transportation is usually just a very small factor. Let me give you an example for a revamp of an axial compressor that MAN performed a couple of years back. The original equipment was installed in the 1990s. It's a refinery in the Middle East, and we're talking about a A45-11 compressor. A4515, that was the former Sulzer turbo code and actually means axial for axial compressor. 45, that's the diameter of the shaft in centimeters, and 11 is the number of stages. The reason for that revamp was one of the most common aspects, increasing plant size, increasing production. Looking at the setup, we were talking about that compressor here, A45-11, which was coupled with a flexible disc coupling and driven by a steam turbine. We were talking about a pressure ratio of about 3.5 from atmospheric to 3.5 bars absolute discharge, pressure about 90,000 norm cubic meter air, and we do have a speed controller to handle and to control that compressor, which is pretty normal for steam turbine driven equipment. Looking into the figures of that plant increase, that resulted in, first of all, in an increased pressure ratio for the compressor. So the plan was to increase the pressure ratio by 20% to go up to 4.2 bars absolute discharge pressure. And the main factor actually was the flow increase. We're talking about the flow increase from 34.5%, which is a major increase for turbomachinery equipment. Eventually, of course, that results in a higher power consumption, and the turbine needs to be looked at as well. Looking at the thermodynamics, this is the map, the original map, as we saw it before, with the original design operation point where the unit was running. The new design point had a higher pressure ratio and a higher flow up here. This was the new map after the revamp. How could this be done? It's a major change, and what was necessary to be exchanged on that existing compressor to meet that target? Here we see cross-section of the original compressor and the revamped design. First thing that was exchanged was the blading. New, we used 13 stages instead of 11 stages to deliver that required increased pressure ratio. And there was a new blade profile. A newer state-of-the-art blading was installed for that blading from 1990, which had a very much higher polytropic efficiency and was specifically optimized for high flows to be able to push this additional 30%, 35% of flow through the compressor. In general, the flow channel needed to be increased. It was not possible to throw this additional 35% through exactly the same flow channel. That would have resulted in too high speeds and gas velocities. Therefore, it was necessary to open the mouth of the flow channel and replace it by a larger design. Last but not least, we needed about 32% additional power to do that compression. So the turbine had to be adapted as well. And we had to replace the second stage, which was the throttling stage of that turbine to be able to supply that power. In general, all the rest could be retained. So it was not necessary to touch the outer casing. The shaft could be reused, seals, bearings, coupling, unchanged oil system, and retained anti-surge and safety valves, which were sized from the initial installation for quite large sizes, which is usually not the standard, but can be the case every now and then. So considering the amount of modifications that were done for getting that much more out of that unit, it's quite impressive. Just another second small example. a unit in South Korea in 2018 where the goal was to increase the efficiency of the equipment, and by replacing all these inner parts you can see here, the greenish parts, it was possible to increase the efficiency by about 6.5 to 7.3%, which is a one-to-one power saving, which results in 7.3% lower operation costs. Talking about centrifugals, now we're going to do exactly the same game as we did for axial compressors. We're looking at the internal part of a centrifugal or radial compressor. For your explanation, this is the compressor inlet, the nozzle where we feed through the inlet guide vane into the first impeller, go through the first stage diffuser, return channel, second stage, second impeller, diffuser, return channel, in series through all the 6 impellers until we feed into the discharge volute, which can be seen here.
Yeah, Marco, it's about 1232.
Thanks for that.
Thank you.
We do exactly the same game again. We see the original performance envelope. As before, we're going to increase the speed. And I guess all of you can already imagine what's going to happen. Thermodynamics doesn't change, aerodynamics either, from one compressor type to another. We move the operating range along the surge line, upwards and downwards. The second option is basically diffuser modifications. And this is something that is not really possible for common axial compressors. And for that, we look at the front eye of a compressor stage. What you see here is basically the impeller, and around here, this is the diffuser with the diffuser vanes. In this case, they are adjustable to basically demonstrate the changes. Looking at this white area that is highlighted here, once again in green, these are simplified visualization of the impeller, of this diffuser vanes. In the regular setup, they result in that reddish envelope, the original envelope. What happens if we remove them? If we remove the vanes completely, we just cut them out. We're going to end up in a so-called unvaned diffuser. Unvaned diffuser means that we're going to increase the flow path. We basically remove the vanes that limit the flow that can be handled through the diffuser, and therefore we increase the throughput by a certain amount, which can be quite a bit of an increase. However, the flow is not as properly guided as if there was vanes installed. So therefore, the efficiency drops. And drop in efficiency means less pressure ratio. So long story short, removing the vanes means more flow, less pressure, less efficiency. At the other hand, what we can do, we can close the vanes or we can open them. For this example, we're going to alter the vanes and close it by a certain amount. If we close it, if you remember what I just mentioned a couple minutes ago, we're going to close the flow path, we're going to smaller the flow path and therefore limit the throughput through the diffuser. That results in a lower flow, and we actually shift the map towards the left side throughout lower flows. At the other hand, we do have gas flow very well guided, as basically the cross section through the vanes or in between the vanes becomes smaller. That means we do have a better guidance and we gain efficiency and therefore we gain pressure. So in this case, closing the vanes to a certain amount means less flow, higher efficiency, higher pressure. Last but not least, of course, we can combine all those options and rebundle the whole compressor. Remove rotor, remove internals, and this gives us, that was too fast, the full flexibility to basically move in any direction we want with the performance envelope. Another example here, a platform in the Caspian Sea. Due to the service was flash gas compression. It was a RB35-7. That means a radial compressor of a barrel type, 35 centimeters medium diameter of the impellers and 7 stages. There was the demand for increased production, same as for the axial compressor, and the gas has slightly changed. Looking at the setup, same again, we do have a compressor driven by gearbox, and in this case, an asynchronic motor. Looking at the conditions, the pressure ratio remained more or less the same, from 2.55 to 2.46, roundabout. That's considered the same. The flow has significantly increased by 50%, and the mole weight a little heavier, and as a result, the speed and the power demand from the driver has changed as well, but I'm going to mention that just in a sec. As before, this is the original design point that moved over here to the right-hand side. Slightly lower discharge pressure. Remember, the pressure ratio remained the same, but the overall pressure ratio slightly dropped. Therefore, this is why you can see that vertical difference between original design point and the new operation point. In this case, we basically added 50% of flow, of volume flow. We look at the setup again. This is the 7 impellers. Now we look from the other direction. We start at the right-hand side, and the discharge value is at the left-hand side, but the setup is pretty similar to the example I just mentioned before. So the problem that we faced here is the thermodynamic requirements of that revamp was we had an increased volume flow of 50%, which is major, but the pressure ratio remained unchanged. So having 50% more flow means actually wider impellers, and that would mean we do have more axial space that would be required to install these wider impellers. But we do have physical limitations. That means the outer casing is given. There is just not more space available on that offshore installation. We have to use what's available. So we need more. We need wider flow, wider impellers for the higher flow, but we need the same amount of stages, the same number of stages. So we're running a dilemma. How can we overcome that? That is the big question. The only solution for this revamp was to remove the whole bundle. So what you see here in red is basically the bundle that was pulled and needed to be replaced by a new, different bundle. Looking a little more into the details of these two bundles, first of all, we used to have 7-stage bundle originally, and we ended up in a 6-stage bundle with 6 impellers only. How's that? We need the same pressure ratio. So the 6 stages that were installed now are of a different type. They were actually wider in length, a little larger in diameter, so it was really maxed out to fit it into that existing casing to get to the very same pressure ratio with less stages, but wider diameters. And we're talking here about 10, 15, 20 millimeters of wider impeller diameter. multiplied by 6 stages is quite a bit of an impact. So it multiplies that little wider diameters for all the stages, results in the same pressure ratio. Besides that, that was not enough. We had to replace the gearbox. The pressure ratio and the higher flow required a higher speed. So the speed was increased by approximately 10% with a new gear wheel set. Casing of the gearbox could be retained. It was just a new gear wheel set. And another major modification that was required, the motor. The driver, the electrical motor, needed to be replaced by a new electrical asynchronous motor with a higher power rating of additional 20% power. The old one could not be operated accordingly. To eventually guarantee and ensure that the process targets and that the revamp targets were met, it was a mechanical running test performed on site. That means the equipment was shipped on site, and according to API, an on-site test was done. That means a 4-hour running test with vibrations measured every 30 minutes according to a specific procedure. They needed to be recorded, and vibration and temperatures are not allowed to exceed a certain value. Otherwise, the test is failed and the compressor would need to be make good again. Same applies for the performance. So the performance was actually measured on site and verified if the guaranteed conditions were met within certain polytropic and volume flow and power limitations that are actually given by API and ASME PTC10, which are the test nomenclatures. I talked a lot about major modifications now. It does not always have to be a major modification that is done on turbomachinery equipment. Sometimes even small improvements can help a lot and can help save money, energy, or to lower emissions. We're just talking about lube oil quality monitoring can help a lot, improvement of lube oil quality, upgrading from seals, from one seal type to another seal type, or control system upgrades. These are all smaller modifications that can be done, but can help to save a lot. So each modification is basically very tailor-made to the needs and the existing boundary conditions on site. So whenever you feel or see there is a need, or there could be an opportunity to save costs, it might be worth to look into it. Let's just spend a few minutes on OMNICARE. The compressor, at one time, they approach the end of their lifetime. Can be 30, 40, 50, 60, 70 years. We even have equipment that run for 90 years in Canada, by the way. But at one point, it's just time to think about what to do with that equipment when it comes to replacement. Option one is what we talked about quite a bit, retaining parts and just replace certain parts, mainly internals of the existing equipment. The second option is basically reverse engineering. We just take that old installation equipment and we reverse engineer it, copy paste, throw it in, go back to operation. Usually not the best solution. It's quite expensive and doesn't provide any additional advantages. And we're not going to get in the state-of-the-art design. So at one point, even a footprint replacement of the whole equipment, of the whole compressor, for example, can become a valuable option. In this case, it needs worth to look into it. We basically start from top and then dive deeper and deeper into the details. First of all, it's important to have as many information about the equipment as possible, from manuals to site visit, to know the boundary conditions, to see the nozzle setup, to see the center line height of the equipment. This all needs to be considered, and then we come up with a plan and a solution how this can be replaced. The process is usually exactly the same, regardless if it's an equipment from Sulzer, MAN, GHH, or any other manufacturer in the world. In the beginning, data needs to be gathered. We know the boundary conditions from site. We know where the compressor wants to go. Maybe the conditions remain the same. That's already enough information. With this input information, there's usually a so-called feasibility check done, compressor selection layout, just on a high level, what could be done, what would be the house number, the rough figure for that revamp.
Marco, it's 1:45.
Yes, sir. Thanks for that. With those preliminary information and the high-level investigations, it usually comes to a budget price. What would that end up with? If that project is then still considered as economically beneficial, there's usually a more in-depth engineering study done, which ends up in a firm proposal, a confirmed layout, guaranteed operation conditions, and basically with a proposal that is ready to go into the final negotiations. Just a small example about such a footprint replacement that was done a couple of years back in Apache Forties field, which is a field in the North Sea near England. And we're talking about 6 old compressors from a different manufacturer, originally from the 90s. And the problem with this equipment was they had a very, very deteriorated performance over the years of operation due to corrosion, due to just a dirty service they had to do on site. And from that original OEM, there was just a very poor service available to service these equipments. I do not have too many good pictures of that revamp. However, it's worth mentioning it. What you see here on the right-hand side, it's basically the footprint. You see the 4 pedestals at the corner of the unit. These are the 2 flanges, inlet flange, discharge flange, and this setup had to be met with the new compressing equipment. So the solution for that was we installed 6 barrel compressors, RB35 type with 8 stages, including 6 different individual dry seal racks, including booster racks and 2 generators and all the, call it, common stuff that comes with such a major change on a platform. So it was really basically throwing out the old equipment, installing the new one. Of course, a certain shutdown was required. We're talking about 6 compressors, but they all took over service and are running well since about 8 years now. That brings me to the end of my presentation about revamping turbomachinery, about revamping compressors. I hope I could give you a little insight where it starts with the thermodynamics. That's usually giving the boundary conditions for the mechanical design, which is usually very limited because of the given boundaries from site, and eventually all the different systems that need to be looked at when going into such a revamp process. I hope you enjoyed that session. I would like to thank you for your time. Whenever you have any questions or idea, do not hesitate to contact us. We're here to help and happy to look into possible modifications of your equipment. Thank you. And now we do have time for Q&A, whatever you've got on your heart. Raise your questions, please.
Thank you, Marco. That was actually, yeah, quite a good presentation. A lot of different scenarios, and going through seeing the compressor map was really interesting too, to see what changes affected the performance, what ways. So we do have a list of questions here that I'll go down through. So Nurud Chowdhury asks, what are the limitations for revamping axial compressors?
Can you repeat that, please? Now you were breaking up for a second.
Oh, he was just asking about the limitations about revamping axial compressors.
All right, let me go back to the corresponding slides to answer that question properly. It's always good to have a corresponding compressor on the screen. So
Yeah, the next question was fairly similar to there, Andrew, from Sharif. Was asking what's a typical limit to revamp without changing the casing and nozzle arrangement, which is, I suppose, a subset of that more general question.
yeah, let me throw that slide. So this is the cross section of the axial compressors. Actually, there are several different boundary conditions we have to look at. It was pointed out the nozzles. So at one hand, we do have the thermodynamic and the aerodynamic limitations. So that means within the nozzles or within the whole compressor channel, we cannot exceed a certain velocity of the gas velocity. Long story short, regular axial compressing equipment runs below the velocity of sound, which is 330 roundabout meters per second. Because when approaching that velocity of sound, we hit the stone wall and the gas itself starts to block in the flow path. It basically creates turbulences and you just lose efficiency and the gas heats up and you're not gonna push more flow through it. So at one hand, there is a thermodynamic limitation in regards to that, in regards to the velocities. Another thermodynamic boundary condition, for example, is temperature. Compressing gases results, Joule-Thomson effect results in high temperatures. I wish we could compress up to 500 degrees C. Unfortunately, we would have issues with the material specialists when heating the equipment up that far. So temperature is always a limitation. At the other hand, we do have mechanical limitations. So we cannot speed up the shaft as far or as high as we want. At one point, we basically exceed the tensile stresses of the material and then we would risk the blades to fail. So long story short, we can say we do have mechanical boundary conditions and we do have aero and thermodynamic boundary conditions. In regards to limitation from the casing size, it's a previous simplification. We can say that the more flow we put through it, the larger the casing needs to be. And the higher the pressure ratio, the more stages we're gonna need. So depending on the given casing dimensions, we can just boost it up to a certain limitation. And then it's just physically not possible to go above that because we would then hit once again the aerodynamic or the mechanical limitations. And same is basically the limitation for the stages, for the length of the equipment. And one point before I forget it, rotor dynamic limitations. I wish we could build a very, very long, very thin rotor, would be the best from thermodynamic perspective. Looking at from a rotor dynamic perspective, I guess our rotor dynamic specialists would kill me for coming up with such a revamp because it's just not stable. It will not run and it will end up in high vibration and eventually in corresponding trips.
Thank you. Okay, and there's another one here. In a 4511 revamp, was the replaced impeller length the same as that of the original impeller? And if yes, how can the casing, I'm not quite sure what he's saying here.
Well, it went from 11 impellers to 13 impellers.
Yeah.
So this is the example. It's actually a very good question. As you can see here in the original design, there was a lot of space left. And but only 11 stages were installed back in 1990 when that compressor was originally installed. And the reason for that is that casing in 1990 was of a cast design. And back in the days, there were standard casing models used for casting the outer casing. So in this case, the owner of that equipment was actually fortunate that back in the days, they had to use a larger, a longer casing, which is basically heavier, a little bit more expensive, but provides much more room for modifications in future. So if the original compressor would have been an AV45-10, it would have been possible to go for the shorter casing with the same diameter, but the distance between the nozzles would have been shorter. So it would have been a little cheaper, but it wouldn't have given the opportunity to do such a revamp. So in this case, fortunately, there was plenty of space available within the casing. And as you can see here with the 13-stage design, there's even space for adding 1 up to maximum 2 additional stages. But of course, it can as well come out the other way around. When it fits in a smaller casing, there might be limited options to boost the flow and the pressure ratio that much as it was possible in this case.
If I could add one more variable there, the diameter, if you see the outer side, hasn't changed, right? So the diameters that we're talking about, blade lengths and all that, are probably almost the same. It's just a blade profile that has been optimized now with newer manufacturing methods and newer engineering. It allows us to engineer these quite a bit more efficiently, so that the profile itself of the blade is different, that allows that extra flow to go through and that extra pressure to be built.
To add to that, the rotor, the shaft diameter was exactly the same. Basically, Martin, what you mentioned is correct, but as you can see, as the stages were moved from the center of the compressor to the front of the compressor, we basically increase the first stage length just by the given fact that the flow channel is like a mouth and getting smaller through the compressor.
Okay, we have maybe only 2 minutes left, but there are quite a few questions here. So, as mandated revamps only for air or process gas as well in axial machines? And so I think the answer is yes, process gas as well as air, right?
Yep, that's correct.
Revamp of barrels, centrifugal compressors, can we fit IGV capacity control? Another question.
Into existing compressors, it's basically not possible. Reason for that is that the space limitations within a barrel compressor are usually quite tough. Let me pull that drawing once again. So that was this one. First of all, we do have the spatial limitations. So the IGVs would have to be installed here within the vertical inflow into the impeller. However, to have IGVs, proper IGVs that basically guide the flow into the impeller, the vanes would have to be installed here in that area, axially in the inflow into the impeller. And this is, first of all, from the mechanical point of view, very difficult to put it into a bundle like that. Then it's just a source of many difficulties. You will have many small parts, moving parts, which are at risk to fail. And we want our equipment to run for years without being opened, without being shut down. So it's basically a question of availability And last but not least, in most cases, barrel compressor are either driven by a turbine, which is speed controlled, and there's no benefit of IGV over speed control, or by motor with VFD, or they run that steady that it doesn't not really pay off to install IGVs and just a suction throttling valve is installed.
Okay. So I don't know, well, we do have a few more questions. I think maybe what we'll do is, for the sake of time, we'll cut it off here, but we'll include the questions and the answers in our LinkedIn, event or the group. We'll pick somewhere in there to kind of add some comments in there. And of course, if anybody has any more further questions, we can continue on that conversation in LinkedIn as well. So anyways, thank you very much. Again, this was a really good insight into revamps for compressors. Stay tuned for next month. We've got Alberta Governor, who's doing surge protection and compressor controls. So does anybody else have anything before we sign off?
Yeah, Ralph here. I just wanted to say that RATS exists through the support of our sponsoring companies, and MAN is one of our sponsoring companies, and do want to thank them for allowing us to be able to continue doing these technical presentations and a number of our other activities, including scholarships. And so they're important to our ability to do these kind of activities for the rotating turbo machinery community.
And from my part, thank you very much for the opportunity to present this information. I just wanted to also emphasize this is, as Marco mentioned, general application for any kind of compressor, and sorry, our capabilities are for not just MAN equipment, but in general, any compression needs that you might have. So just to keep that in mind. But thank you again for the opportunity to show this information, and thank you for RATS, Andrew and Ralph, for the opportunity as well.
Thank you.